Hello. With this presentation, we'll be discussing and sharing our assessment of the data regarding chocolate and specific key factors and how we can use this data to predict what is the best candy to introduce to the market. Chocolate is a big global business. According to a recent survey from the U.S. National Confectioners Association, over $12 billion was spent on chocolate in the United States alone. We are a group of business analysts for a new candy T-Bird Chocolate Company, which is a new startup that is trying to decide where to source ingredients for chocolate and the best type of candy bar to produce for a global market. Our task is to create the perfect global candy bar. A little history about the chocolate to make this more enticing. Chocolate may be the food of the gods, but for most of its 4,000-year history, it was actually consumed as a bitter beverage rather than a sweet edible treat. It is found evidence that chocolate was produced by pre-Olmec cultures living in present-day Mexico as early as 1900 BC. The ancient Mesoamerica's first cultivated cocoa plants found in the tropical rainforests of Central America. Fermented, roasted, and ground the cocoa beans into a paste that was mixed with water, vanilla, honey, chili pepper, and other spices to brew a frothy chocolate drink. Our goal in this analysis is to analyze and decide if a candy with chocolate is more popular in the direction we want to look to go. Additionally, if this is the case, we want to determine where the best ingredients should come from, if the presence of chocolate in candy is more favorable, as well if more ingredients make for a better candy to launch. Our intended outcome is to be confident in entering the global market in the world of chocolate candy providers. In order to reach this goal, we came to this research by making the following hypothesis. We have taken each of these hypotheses and done some analysis on them, which we will discuss in depth on the upcoming presentation. In order to test these hypotheses, we needed data. This data was provided to us by the instructors, and they include the following: the candy data file and the flavor of cocoa file. Data reference material is provided within this slide. Within these data sets, there are variables that we used in order to get our analysis. These variables include cocoa percent, ratings, bean, country of bean, and chocolate. The variables continue on to the next page. This includes fruity, caramel, peanut almondy, crisp rice wafer, price percent, and win percent. These all are either nominal or scale variables. However, the main variables we utilize in our testing we want to focus on are the percent of sugar it falls under within the data set, the unit price percentile compared to the rest of the set, the overall win percentage according to 269,000 matchup of candy, does the candy contain chocolate, flavor of cocoa, specific cocoa type bean, bean location, and if all the ingredients determine flavorability. Before we get into the analysis of the data, we want to express some of our concerns. First, we want to address the fact the length of time of completion of data ranges from 2006 to 2017, which is a large time frame and could be inconsistent. Another concern that we have would be the fact we cannot show any definitive documentation of any controlled data being completed. This could affect our hypothesis outcomes as we only can make assumptions. Properly collected and archived data continues to be useful as new research questions emerge. In fact, some research involves reanalysis of data with new technology, different ways of looking at the data, or combine the results of several studies. Next, we determine the steps in the process. We've broken this down into 4 parts of determine, organize, run, and analyze. First, we determine what tests will need to be conducted. Second, we organize the data for each test. Third, we run the test in SPSS. And fourth, we analyze data to determine alternative hypothesis or continue with the null. This process will allow us to compile and analyze effectively and efficiently. Now on to the data. When looking at data sets, one of the first steps you want to do while analyzing your data is to make sure your data is normally distributed, and that could be done in multiple ways, but as shown in our histogram graph with bell curves, we did an explore analysis and a frequency analysis to determine if our data is normally distributed. We're going to take the first look at our CANDY data file, and at first glance at our charts, you may deduce that normality based off of looks. But if we dig into each individually to determine normality, you'll see a difference. Looking at price percentage, at first glance, you would have a hard time telling if there's any skewness to this data, as the bell curve is right in the middle. But taking the skewness divided by the standard deviation of skewness, you'll get a 0.51 z-score for skewness. And since it is under 1, that means it has a positive skewness, but it's relatively symmetrical. Looking at the kurtosis, you get a z-score of negative 2.22, which you can see in the width of the bell curve as being too wide, making the data not normal. This can be validated in the SW score of 0.001, stating the data is abnormal. Moving on to sugar percentage, as you can see, you will run into a similar situation as price percentage, where the z-score of skewness is at 0.36, which gives a positive skew and symmetrical. But when you look at the z-score for kurtosis, you get a negative 2.19, which, as you can see in the similarities, the bell curve is too wide and the data is not normal. This can also be validated in the SW score of 0.004, stating the data is abnormal. When looking at win percentage, you can guess right from the start that the data seems like it is normally distributed, and you'd be right with an SW score of 0.139, making it above 0.05. But if you take more time to look at it, you can see the skewness of the data is leaning a little to the right, meaning there's a positive skew. The z-score for skewness is at 1.27, and the z-score for kurtosis is at negative 1.12, which means it's not ideal for skewness and kurtosis, but it proves normal distribution. The last one in the candy dataset is chocolate candy, measured with a 0 for no chocolate in the candy and 1 for chocolate in the candy. The z-score for skewness is 1.019, which is an acceptable positive skewness, and a kurtosis z-score at negative 3.8, which is above the acceptable rate of 2, and it makes the data abnormal as shown in the SW score of 0.000. Moving on to our second dataset with flavor of cocoa dataset, we have two variables that were measured for normality. The first one we're going to take a look at is cocoa percentage. At first glance, you can see some extreme values that cause skewness in the data. Digging into this data, we were able to determine that the data was necessary as part of the sample. Continuing on, we determined the z-score for skewness was at 1.82, which is an acceptable value to prove normal distribution, but looking at the z-score for kurtosis, it was a whopping 43.06, which makes it definitely abnormal, which is shown in the SW score of 0.000. Going on to the second variable of rating of candy, you can see some extreme values in the one like cocoa percentage, but we determined these values as necessary in the sample and we continued forward. Looking to the z-score of skewness, we are at a negative 0.99, which is the only negative skewness level we have in our variables, but it's within acceptable limits. Looking at the kurtosis z-score, we get a 9.86, which makes the data abnormal, as well show as the SW score of 0.000. The main purpose of doing all of these normality tests is to determine whether we can use a variable in future tests that may require the variables to be normally distributed in order for the test to run correctly. As we determined, the only variable that is normally distributed is the win percentage within the candy data. All the rest are abnormally distributed. Besides the main purpose, this also allows us to get more familiar with the data as we're working with it. As you can look at the current slide, you can already determine that most of the candy bars only have 70% cocoa in it. You can also determine means that can be used to help along with the data analysis down the line. After running the normality test to determine normal distribution of variables, we move on to test our first hypothesis with our null hypothesis stating the type of cocoa bean does not have a significant association with the rating of candy with a p-value greater than 0.05. An alternative hypothesis stating there's a significant association between the two with a p-value less than 0.05. We look into creating a global candy bar. It's important to know the type of cocoa plant plays into part. We test this hypothesis by using a chi-square test that allows us to test the relationship between two variables. In our case, we have a nominal and a scale variable. Running the chi-square test, and the first thing you will look at is the red circle, and you can see that 91.4% have expected count less than 5, which means the chi-test assumption has been violated. This is due to the amount of non-reported cocoa bean types in the dataset as shown in the snapshot at the bottom. Because the assumption was violated, we would then determine our hypothesis looking at the likelihood ratio in row 2. And with that being at 1.0, we can now accept the null hypothesis stating the type of cocoa bean does not have a significant association with the rating of candy. Continuing on, we want to be able to see what our selling price should be based on the win percentage showed in our candy bar data. Our initial null hypothesis will state that there is no correlation between win percentage and price percentage in the candy bar data file with a p-value greater than 0.05. With an alternative hypothesis saying there is a correlation between the two variables with a p-value less than 0.05. To analyze this hypothesis, we ran a bivariate correlation analysis in SPSS with these two variables to get an answer shown in the slide. As you can see looking at the data, we highlighted the important information with a blue circle, and you can see there's a correlation coefficient of 0.345 and that our sig value or p-value is at 0.001. Which would seem like we can reject our null hypothesis and accept the alternative, that there is a correlation between price percentage and win percentage. But looking at this chart, it's hard to determine that there is a correlation relationship between these two variables. That is because in previous slides, we determined that win percentage is normally distributed, but price percentage is abnormally distributed. Because price percentage is abnormally distributed, we are unable to use bivariate correlation analysis used in the previous slide as both variables need to be normally distributed in the data. This ensures the variables are linearly related, and violations of this indicate that non-linear relationships amongst variables exist. Because of this, we then determined that we must accept the null hypothesis that there isn't a correlation between price and win percentages due to price percentage being abnormally distributed. Moving on to our next analysis, we want to determine linear relations between sugar percentage and win percentage. Our null hypothesis would be there is no linear relationship between sugar percentage and win percentage in the candy dataset, and our alternative hypothesis would be there is a linear relationship between the sugar percentage and win percentage in the candy dataset. This test would be done running a linear regression analysis. After running the analysis and looking at the statistics, we want to see if all assumptions are met to interpret the regression. Looking at the correlation analysis and the regression analysis and see that the p-value is less than 0.05 at a 0.017, which means there is correlation between the two variables. Moving forward, we want to determine normality, which we determined earlier that our dependent variable, win percentage, is normally distributed, and you can see also looking at the PP plot line that is presented that is plotted along a 45-degree line. You can also see homoscedasticity with our two graphs shown elliptical and that there is no pattern presented. Since the assumptions are met, we can use the regression analysis data to look at our coefficient table. The table determined our hypothesis by looking at the sig column to determine our p-value of 0.035. Since it's less than 0.05, we can reject our null hypothesis and use our alternative hypothesis that there is a linear relationship between sugar percentage and win percentage. Because we're able to see linear relations, we can determine the regression model of coefficients, which is shown on the slide as a win percentage equals 44.6 plus 11.6 times sugar percentage. And we can also state that for every standard deviation change in sugar percentage, there's a standard deviation of 0.229 standard deviation change in win percentage. For our next test, we want to determine that having chocolate within our candy will have an impact on the overall win percentage compared to candy that doesn't. Using the data from our candy data file, we want to compare means of candy that has chocolate in it compared to candy that doesn't. Going off of the data, we can see that candy bars that have chocolate in them are a nominal variable and the win percentage is a scale variable. This will allow us to run an independent sample t-test to determine first, using the Levene's test for equality of variances, producing a null hypothesis if the p-value is greater than 0.05, then the variance is not significantly different, and we can assume that they are equally distributed. With an alternative hypothesis of a p-value lower than 0.05 showing the variances are significant and that they are not equally distributed. This basically means that in the sample of data we have close to equal amount of representation of candy that's chocolate in it to candy that doesn't. Second, we want to determine the null hypothesis of the average win percentage between candy that has chocolate in it to candy that doesn't have chocolate in it do not differ from each other, with a p-value of greater than 0.05. With an alternative hypothesis of candy with chocolate and candy without chocolate do differ from each other, with a p-value less than 0.05. This showing a significant advantage in our initial assumption for candy that has chocolate in it. Running the test in SPSS, we determine the test variable is win percentage and the group variable is chocolate, defining group as 0 equaling candy that doesn't have chocolate in it and 1 equaling candy that does have chocolate in it. Once the test has been run, we first want to determine our first hypothesis on whether the variance between the two groups are significant or not. Looking at Levene's test table, we can look at the sig column circled in red, and we can determine our value at 0.077. And since it's higher, we can determine that our null hypothesis is correct and that our variances are not significantly different, and we continue ahead in the top column of the t-test with equal variances assumed. Moving on to our second hypothesis, we want to look at our t-test for equality of means. Since we have proven that the variance is equal, we will look at the sig value in the first row, circled in green. We can see that the value is 0.000. The value is less than the p-value of 0.05, which means we can reject the initial null hypothesis that the candy that has chocolate in it does not differ from the candy that doesn't have chocolate in it, and go with our alternative hypothesis that they do differ. Since they do differ, and looking at the mean in the group statistics circled in blue, we can determine that candy that has chocolate in it is significantly different and that it can have a positive impact on the candy bar. Continuing on with running t-tests, we wanted to determine if the cocoa bean that was pulled from multiple locations have a higher rating than cocoa beans that were pulled from one location. Using the flavor of cocoa file, we wanted to continue using the independent t-test to compare the means to determine. Like the test before, we wanted to test using the Levene's test for equality of variances to see if the test produced a null or alternative hypothesis. That basically means that in the sample of data that we have close to equal amount of representation of cocoa from one location compared to cocoa from a multiple location or not. Second, we wanted to determine the null hypothesis of rating of cocoa at one location to rating of cocoa in multiple locations do not differ from each other, and an alternative hypothesis that they do differ. This showing a significant advantage in our initial assumption for cocoa from multiple locations. Before running the test in SPSS, we need to determine the group variable. This required us to create a new variable called multiple country count. If only one country was represented, a 1 was put in. If more than one country was represented, then a 2 was put in. If a country field was empty, we left a variable empty as well. Now that we have a good variable to build off of, we went into SPSS under the independent t-test. We made the test variable as ratings and the group variable as the newly created variable multiple country count. Once the test has been run, we first wanted to determine our first hypothesis whether the variance between the two are significant or not. Looking at the Levene's test table, we can look at the sig column circled in red, and we can determine that our value is at 0.086. And since it's higher, we can determine that our null hypothesis is correct and that our variances are not significantly different. And we can continue ahead in the top column of the t-test with an equal variance is assumed. Moving on to our second hypothesis, we want to look at our t-test for equality of means. Since we have proven that variance is equal, we want to look at the sig value in the first row circled in green, and we can see the value is at 0.086. This is more than the p-value of 0.05, which means we have to accept the initial null hypothesis that cocoa from multiple locations does not differ from cocoa from one location. Even though when you look at the blue circle and see means that are higher for multiple locations than one. We asked ourselves if we felt that the percentage of cocoa in candy would have an impact on the public rating. As a way to determine and find the answer, we ran a one sample t-test to determine whether the sample mean is statistically different from a known or hypothesized population mean. This will tell us our hypothesis regarding public rating of candy is impacted by the percent of cocoa in that candy. This is a two-tailed test because we are testing for a difference higher or lower than 95%, the level of significant p-value. In this case, we reject the null hypothesis that the percentage of cocoa in candy will have an impact on public rating, as there was no significant difference shown. Therefore, we can conclude that the amount of cocoa percent in the candy does not have an impact in the public rating of candy. Continuing on, we asked ourselves that candy with 4 ingredients in it is a favorable choice for our new candy bar over candy with only 3, 2, or 1 ingredients in it because of the high win percentage average. We ran this in as a ANOVA analysis because we have 2 or more groups. So we go into analyze, compare means, select the ANOVA dependent as win percentage, and the factor as ingredients, and we select Tukey in post-hoc analysis to help us determine our hypothesis. What did we get in the significance ANOVA? 0.000. So that means there's a difference in the win percentage among the number of ingredients that the candy bar has. Now we want to know which groups are different. Subsets were found that those with 0 and 1 ingredients have the same win percent average, and those with 2, 3, and 4 ingredients have the same win percentage average. Therefore, ingredients with 0 and 1 are different from ingredients with 2, 3, and 4. As you can see, the highest one is for ingredients of 4, and then ingredients of 3 is the second highest one, and so on. Therefore, the hypothesis is proven that the candy with 4 ingredients is favorable. After looking at the various testing and hypotheses drawn, we can bring together the data to present it to our candy bar company on the best globally loved candy bar. In our first test, we tested for normality and distribution of all used variables, and we found out only one is normally distributed, and that was win percentage. On our second test, we discovered that cocoa beans do not have a significant association with the rating of candy. In the third test, it showed there is a linear relationship between sugar percentage and win percentage in candy dataset. The fourth test showed chocolate in candy bar is significantly different than candy that does not have chocolate, and it can have a positive impact on the candy bar itself. The fifth test showed cocoa pulled from multiple locations are not significantly different than cocoa pulled from one location. The sixth test showed that the amount of cocoa present in candy does not have an impact in the public rating of the candy. And the seventh and last test showed that candy that has 4 ingredients in it are more favorable than candy that only has 1, 2, or 3 ingredients in it. Bringing all this data together, we can come up with a final recommendation to present to our candy company on a globally loved candy bar. With our final recommendation, we would recommend that the candy bar would include chocolate in it, and the candy bar would have 4 ingredients in it, like a Snickers bar. The candy bar would also have a high sugar percentage, as it linearly correlates with the win percentage in candy bar. When looking into getting cocoa for these candy bars, we would let them know that there's no correlation between bean location, type of bean, and cocoa percentage in the candy bar that will have a direct effect on rating, so they're open to gather their cocoa from any location and any type. All of this will help our company in ways that were not possible in the past thanks to data analytics. Please feel free to reach out to me, David, or Shauna with any questions through our ASU emails on this presentation. Thank you.